Hello everybody. I got a request from somebody on the Atari Age forum on Facebook to ask specifically how I am writing code on PLATO using the TUTOR language. So I'm putting together a quick video showing the workflow of doing just that. So we'll go ahead, and in order for us to do this, we're going to go and use a pterm session over here on my PC connecting to the PLATO network and go through the process of entering code, of condensing it, and seeing the results, along with a few examples. So with that, let's go ahead and start. We see here our pterm window ready to go. Go ahead and press next to begin. Log in. And with that, we have dropped into author mode here. Now, in order to start, you can't just start writing code. You actually have to have space allocated to you by the system operators. To do that, you drop a note into the requests note file. So we go to request, and this is specifically so that the system operator can take and create files for you, storage spaces where you can put your tutor code and its associated resources. So with that, you notice we only have write-only access to the file. We can't see other requests, whatever. Next to write, and all you have to write here is just a basic form of, hi, I need tutor space for the following purpose. That's it. It's really, that's it. That is the base of all you need in order to make this work. So with that, it looks something like this. Tutor or lesson space. Something like that. Doesn't have to be too verbose, but kind of state a purpose. So with that, send it off. Since I've already done this, I'm not going to do it. I'll just back out of it. And wait roughly 24 hours, after which you will receive a personal note indicating the space that you've been allocated, how much space you've been allocated, as well as a default password so that you can access the learning space, so that you can access the tutor space. So since I asked for a workspace, mine starts with my account plus WK for work. I've added security measures here so that other people can inspect the code, and or you can try the code, or in my case, I want to edit it, so I will enter my password in for this one. When this is done, you now have a directory of all of the blocks inside of your lesson file. A block is really not much more than just a delineation of space. You can think of them as subfiles in the same file, which in mainframe terminology is essentially, IBM calls it a data set, controlled data calls it a data set, so you see that same terminology also carry forth into PLATO, because PLATO runs on controlled data hardware. But it's abstracted from you by the system. So if we press one of the letters here, we see one of the subsections. We'll go into the directory, which is the metadata for the particular lesson, and we see a lesson name, when it was started, just the master file that it was built from, the account that it was set on, when it was last edited, and the last change that was made, and where that change was made. We can go into the next bit of information. Hitting next will take and go through each one of these screens, A, B, C, D, and E, one at a time. So we'll go ahead and look through them. And you can see various bits of metadata here. I won't stay on this for too long. And we have here various bits and pieces for associated files. You typically don't need to change these too much. And finally here you have the ability to set very fine-grained security codes for various control aspects, to change lessons, to inspect them, to access the common data, to use the lesson, to jump out to the lesson, meaning that you can, if I were to put this onto Big Jump, that would be, if you selected it from Big Jump, that would be considered a jump out. So using this lesson from other lessons on the system to attach files, etc. So I've set particular passwords for the most basic here, at the very least, to change the lesson, and I've allowed others to inspect it and to use and to jump out, because I want people to use this. So access to system personnel, we can allow that. You can deliberately take and disallow that if you don't want anybody, if you don't want the systems people to be looking at this. You have that right. Access lists, not particularly important for this discussion here. If you really want to know, ask me and I will explain it in more detail later. Finally here, we have a particular character set that we want to associate. In my case, my game uses custom characters which are uploaded to or downloaded to the appropriate terminal at the appropriate time. We have the block containing the characters and the scope. In this case, it's local to this lesson. You can load characters from other lessons as well. Microtables, which are, the equivalent of ancillary font characters that mean special things, like sigma for some, etc., etc. That sort of thing. You can load custom microtables if you need them. Finally, you have editing constants here. You can show how many lines you want to show in the editor at one given time. Space is a special case. It's essentially allows you to have a default view which only shows a handful of lines at a time. Then you can hit space to act as a toggle to expand and see more lines. I really don't care. I want to see as many lines as I possibly can. You can realistically have up to 31 lines visible on screen, so that's what I put. Maximum number of characters per line being 120. That's fine. I kept that as default. The tab settings are set to the tutor language here. It's a good idea to keep that as it is. Indicate and save change mod words, again outside the scope of just basic tutor usage. If you want to know, I will explain that later. The print option. This was used during the days of PLATO when when there were actual running PLATO systems, and you wanted to request and you were at a remote location or somewhere where the printer wasn't nearby, and you wanted to request a printout of your lesson, you could set the particular print options here, print the lesson, and have them mail you the printout at some point in the future. It's not really applicable here. And finally here, this is only really of use if you have code that you want to run locally to a machine that's running MicroTutor. And there aren't very many implementations of MicroTutor that are available here, but suffice it to say, it was a variant of Tutor that allowed you to run parts of or all of a given lesson directly local to the terminal itself. This was especially of use for systems like the PLATO 5 terminal and some CDC microcomputers that had 8080 processors local to them, so you could run code to improve performance. We're not going to be using that here, so it's just there. And I'm not changing the execution mode. This is running from the central system. So with that, we go ahead leave out, and that's the directory. Everything else after this point are essentially blocks that I went ahead and defined. You have up to 7 parts. You have up to 7 blocks per part. You can have, by default, 5 parts. If you need more space than that, you can ask the system operators to extend your space. Now, if we go ahead, for example, I will go ahead and we'll make a new, we will make a new block entirely from scratch here. Let's assume that we have, over here in part 2, I want to make just a testing block or a scratch block that I can mess around with. No problem, all I have to do is hit Shift and the letter close to where I want to insert the part. I want to insert this after C, so I will go ahead and press Shift C. And at this point here, it's giving you a menu of different types of blocks that you want to use. The most common is a tutor block, which is tutor code, which you just press next to go to use. But some of the others are interesting as well. For example, common blocks are very important if you want to have data that will be shared between all of the users of a particular lesson. You need to allocate a certain amount of space for that. Char set blocks are used for defining character sets. Micro blocks are used for defining micro characters. You have vocabulary blocks for defining lists, key value pairs of lists of things such as vocabulary or definitions. Keep in mind, this really makes sense, especially given the fact that PLATO was meant for writing educational software. So they provided a type specifically for this. Line sets are essentially large fonts, except instead of plotting out individual dots, you're plotting out line vectors, essentially to take and do large text type drawings. So anytime you want text in a larger size than the default size, you're essentially using a line set to do so. Listing blocks are basically just explicit blocks of text that are used when outputting to a printed list. Text blocks are uncompiled. They're not touched by the condenser at all. They're used to either store raw text or comments to be used inside the block. Access list block, not applicable here, so let's just go forward. I'll go ahead and create a normal tutor block. What do you want to call this block? Well, I'll call it scratch. And at this point, we are sitting inside of the editor. This may look like a full screen editor, and in fact it is to a certain point. It has more in common with editors like EX, which was the predecessor to VI, than VI. So the way it works might be a little weird for you, but once you go through it a few times, you get it in your muscle memory, you get used to it. You see the particular block number and the you see the particular part number and block 2D, the name of the block, as well as the amount of free space here. Space equals 320. Well, what's 320? 320 actually refers to the number of 60-bit words that are being used to house this particular it's essential to house this particular page. Pardon me here, it's getting late, I'm having a bit of a brain fart. So even though it says that's not 320 bytes, keep in mind on this system the words are 60 bytes long, or 60 bits long. So you can hold with your typical 6-bit characters. That means you can hold anywhere from 6 to 10 characters per word here, depending on whether or not you use any extended characters or the like, that it has to use more bits to encode those things. So with that, we'll go ahead and start entering in some code. Now the editor works off of directives, and we're going to insert some data into the file here. So we'll push the letter I. You can see that the command here has show that we have I, okay, for insert, and we want to insert the first line here, so line 0, at which point we're in insert mode, and we'll go ahead and start typing. Now, most of the time you're writing code in functional blocks called units, and if you're going to reference particular chunks of code, you have to be able to have a unit to associate them with. We'll just go ahead and call this one Scratch. Now, Tutor is very space oriented, particularly with how you have your tabs and things. What I did there was hit Unit Tab Scratch, and that puts the spacing correctly so that Tutor will take and condense the lesson appropriately. If I type, then the lesson will not condense properly. It will think that I'm trying to type a command called Unit Scratch, which is not appropriate. So Unit Tab Scratch, hit enter, go to the next line, and at this particular point we're going to do something very specific here. We're just going to take and start off with doing something that types hello world here. Let's say the screen is 512 by 512. We'll go ahead and just put it somewhere in the middle. And notice I'm hitting tab after each one of these commands. And there we go, right here. Bam, bam, bickety bam. So that's a simple Tutor program. We go ahead and hit back to get out of the insert mode, and we can see now that we have 3 lines that we have written here. So with that, let's go ahead and go back out. Since I'm writing this, I want to take and do a little bit of modification to my code here, and we'll go to a different block. I'm going to minus to go back to the first, minus and plus go forward and back on the blocks, and we will do a define here. And define is where I'm basically putting all of my global bits of information that's being used by the program here. I'll explain some of these other variables in a bit, but for now I want to take and change the initial where the lesson actually starts off here. And to do that, I will use the replace function here. I will replace line 5, R5, hit enter. We can see the few lines before it, and then finally the line that we're replacing. Initial tab lesson will be Scratch. Bam. And with that, we'll go ahead and back out. And in order to test what we have right now, we can go ahead and hit Shift Stop like we would normally use to get out of a particular program in PLATO. But when you're in the editor editing code, what this does is call the condenser to condense the code. Condense is PLATO's term for compiling the code. It's not really a compilation step. Since Tutor is essentially an indirectly threaded language, it's basically just boiling all these individual tokens down into indirect jumps. into various subroutines. So with that, we compile, and we can see, actually, I apologize, it's actually calling my it's calling my old maze data here. So with that, let me take a look real quick. Yeah, data. Excuse me. Let me make sure I get that right. And if you hit Shift F10 again, you'll come back out into the author mode. I will take and make absolutely sure that we didn't do anything really stupid here. Oh, that's why, because we're jumps, because I'm gonna change the jump to jump into my scratch here. So R23, apologies. Back. And you'll notice right here one very peculiarity. It put that last line that I was editing at the top here. If I use plus or minus or up or down arrow, either way, it will move up one line, move down one line. And you'll notice here on the left-hand side these line numbers. These line numbers are not absolute. They are relative to where you are in the window of the file. So you can see it moving down, and line 10 is now MB equals N4. Move down another line, line 10 is MT equals 120, and so on and so on. So let's go ahead and condense this again. And we can see our hello world right there, running, ready to go. Great. So that's how that essentially works. And you can go through now and hit enter to go back to the lesson that you were in. In this case, we were editing our Berzerk here, so it takes me back into the editing environment. And we can go back to the second part here, go back to my scratch, and start modifying, the code some more. There are some interesting, with this, there are some interesting editors that are also sitting on top of this as well. For example, there is the screen designer, which we can get to by typing SD from the editor. And at this point, we have a visual screen designer with touchscreen support that we can use to draw all sorts of different shapes, lines, etc. At any time, you'll notice we see help available. So you can hit the help key, hit help again, and it can show you around all the various bits and pieces of everything that you are. There's context-sensitive help all over PLATO, including and especially in the various programming tools. So graphics creation options. You decide starting points, draw line segments. Create boxes, that sort of thing. So we can go back, shift back. Let's go back again. Let's select a point from right here, no problem. At which point, let's go ahead and let's create a circle. Boom. Or not, sorry. Points. Lines. So you can do all sorts of interesting shapes, lines, etc. And when you're done, you can exit back out, Control B or Shift back, and you will have the equivalent drawing commands popped for you right here inside your code, ready to go. Very handy. So we go ahead and condense again, and we can see our little shape that we knocked up right here. Great. Great. So back in again. Some of the other bits and pieces that you can use include a character set editor. You can see here that I have a particular character set called Berzerk, which is starting to contain the individual sprites used by my game. And I'm going to show you another particular trick here. The editor is touch sensitive, so if I select with my mouse there, or with the touch screen, that particular area, then it takes me right to that particular block editor. In this case, it's a character set, so we have a character set editor. Now, we can look at various things like, okay, how many slots in my character set have been used. You can see individual animation cells here, plus my Berzerk, plus my human character here. You can see what slots are actually available. And as you start using them, entries off of this list will disappear, but it gives you a quick idea of you can use up to 128 some odd characters inside your character set that you can modify for your purpose. I have 120 slots available right now. So great. Go ahead and back. If we edit one of them, we can go ahead and select either a key, which in this case, I know that my first Berzerk character, I repurposed the $sign here, so I will select that one, enter, and we have our character set editor here. Now, I wish this had been touch sensitive, but yeah, you can't have everything. The nice thing is it's easy enough to move around here. But you can see here that characters on PLATO are a matrix of 8 by 16. You can turn on and off each individual bit that you want. You can hit I to inspect your character at any time, in which case it shows up there, along with the original character that you're repurposing here, so that you know which key to press to get that character, and so on. And of course, if you're feeling like you want to enter numbers instead, you can actually enter the data in straight octal by pressing Lab. And you can see the octal representation of the character right here. There we go. Going back. Other bits and pieces include common area. Now, common area is essentially a chunk of shared memory. You have various options here to take and edit it, to change the name of it, to destroy it, meaning to delete it from your file if you don't need it. You can even convert it from a common block to source block, so you can type in data using the editor and then convert it back to common if you want to. It's kind of interesting that way. But we're just going to go ahead and take a look at the common space. I have a lot of variable space here that I'm going to use, but right now I'm only using really 2 or 3 entries. And we can see right here that the default view for common is a combination of alphanumerics on the left-hand side plus the octal representation here on the right-hand side. It's 20 octal digits, which gives us, of course, 60 bits. And in this case right here, each one of these represents a particular common variable, and the primitive names for each one of these are very consistent. This is NC1, NC2, NC3, etc. You can use defines to take and redefine those primitive names into something more palatable. And since common variables are like any other variables in TUTOR, you can also take and divvy these up, segment them off, and use one 60-bit value to hold a whole range of different values. Since you have 60 bits to work with, it's kind of big. This particular common space is roughly about 1,024 words. So think of it approximately like 7.5 kilobytes of data, just shared data. This data is shared between all of the users of the system, and I'm going to be using it essentially to hold all of the state needed for multiplayer gameplay. As I said before, the first variable here is a 60-bit number representing a 5x3 grid containing the maze. So there you go, editing common in a nutshell. You can, of course, modify these values directly if you wish. You can zero them out. You can do whatever you want to inside here. This is a full-fledged editor, just like anything else. So let's say I want to go ahead and word 4, take a look at word 4 there. Alright. I'll say I want to edit word 4. Since I've got alphanumerics, I'll just put my name in there. And you can see now the equivalent octal has been shoved into that 60-bit word. And that's very telling here as to how the system actually stores data. You can store approximately 10 characters, 10 lowercase characters into one 60-bit value here. Just so you know. You can change input modes, and of course help is available. So you can see what you can do here. Yeah, no problem. There you go. So you can change the edit mode, put in integer values, floating point values, or straight octal values, whatever. Doesn't matter. We'll go ahead and return. You can even, if you saw right there, you can even write patterns of data through common if you want to. So with that, that covers the most common, pardon the pun, editing aspects of TUTOR here. And you kind of get a good idea of what it takes to actually take and edit a piece of code here. So we'll go ahead and I'm actually going to go over here to Scratch, and I'm going to delete this particular block. Shift Help is the canonical way to delete something on PLATO. So you press the letters of the blocks you want to get rid of. I want to get rid of block D here. And finally you hit Shift Help again, and that block is now gone. Let's go back, and I will change my defines back again, starting with replace 20. We'll go back. We'll condense the lesson again. And we can see that everything is back the way it was. Great. Awesome. So, with that, I will end this off now by kind of going through little bits and pieces of the code just as a as a small explanation with the time that I have left here. So with that, we of course shift stop again. We go ahead, go back into the lesson, and we'll start here with the defines block here. This is a TUTOR block that I am setting aside specifically for the global parts of the system here, and defining meaningful names for constants as well as meaningful names for variables and the like. Now, these right here are actually comment lines if they start with a C here. It's Fortran style comments. There are other style comments which you'll see throughout the code, such as these here, double dollar signs. Asterisks on the first column also correspond to a comment, and so on and so on. Here we take and define our common area here. We get it from game data, and it's approximately 1024 60-bit words here. LVARs to indicate roughly that we want roughly 1,000 variables for local variable storage. Now let's say you come across something and you don't know what it is, or you're trying to remember the parameters for a particular function or whatnot. You don't have to bounce out of the editor to go to info to see what you like here, to see what this is. You can, of course, if you want to, you can go hit capital Q to go to info. Type in the particular name here, and you will get the full help page right here. Very good documentation. I really have to point out just how incredibly good the documentation is. Throughout TUTOR and throughout PLATO. In the first place, documentation was considered of paramount importance, and it was required that everybody wrote good documentation for the things that they worked on. It was just good culture. So with that, we'll take a shift back again, get out of here again, and back out again, back out, and we're back to where we were in the editor. But you don't have to do that. And I'm going to show you here, if you just want to see the quick reference for LVARs, you could have just as easily done the term key, what term I want some help, and what command do I want to look up. And there it is. Now at that point, it drops you right back into the editor. So if you're editing, you can then start typing at that point here. This just overlays over the top of the screen. And will go away when the screen is essentially repainted. So, of interest here, like say for example, I'll take and we'll go, let's say I want to add an additional constant here. I will insert at line 21. I'll say foo is 21. And maybe I want a segment. But crap, what's a segment? What's the syntax for segment? I could see it right there, but if it wasn't available on screen there, I could just type it in. Oops, sorry. Help. Or define, actually. And you can see the individual bits and pieces here, and you'll see that it dropped me back in, so I can basically say segment is bar, which is equivalent to common variable number 4, and I want each segment to be approximately 6 bits in length, so I can have values from 1 to 64, from 1 to 64, that sort of thing. Boom. Okay, done. So all of that's there, and it's ready to go. So great. Control B, you can see everything goes back to where we were. I really don't want those 2 lines in there, so I will take and delete them out. So D2, and give a range -3 to set a range, and then again, since the global delete key is shift help, and that gets rid of that gets rid of that bits and piece. Now even here, we started with 320 in space for each of the parts and each of the blocks here, and we've gone down from 320 to 230 in this chunk of constants right here. So we can put a lot more constants in here as time goes on, and that will happen. So moving out, we start to get into some of the hairier aspects of the game here. I'm actually going to show this backwards. Let's look at the maze draw code here. And we can see that we have a maze draw, and we have a number of variables here that I'm defining here. Now, if you looked in the defines page, you would have seen define mi equal, mi is this, mx is this, my is this. And I'm doing this so that I don't have to reference n1, n2, n3, etc. These are local variables, they're not condensed. So yeah, I'm trying to give them more meaningful names. And I've set those variables to 0 because I'm about to use them for useful purposes inside this routine. Our origin, if we take a look, it basically sets the origin of the screen for relocatable commands. So drawing commands that begin with an R, you see R at here. That's literally what that is. That's not rat, that's R at. Start at relocatable at 0, 0. I want to take and use the entire screen here, go to this point here, and start setting the color, the display color to blue. And then at this point right here, one very important thing to understand about Tutor is that indexes in Tutor are 1 based. They are not 0 based. Ostensibly to make it easier for non-programmers to understand, but if you're used to doing things counting from 0, it can be rather interesting. Now, we have right here a basic loop construct that I'm using here. It's just loop while this condition is true. It's essentially equivalent to a while do loop in C or other languages of the sort. The main difference here is that looping constructs here are not truly recursive, and thus nested loops do not function the way that you would think that they do if you come from another programming language like C or whatnot. You have to do other things. In this case, what I'm doing here is traversing through, since I'm dealing with a 5x3 matrix of blocks, that's 15 blocks in total. And you'll notice here too, especially, PLATO has microcharacters specifically for things like greater than or equal to, less than or equal to, instead of the usual ASCII equivalent of greater than and then the equal sign, that sort of thing. PLATO also has subscripts and superscripts, so you can, do real mathy type things, and it accepts those things pretty well. Now, we set the new origin here, mx to, we set the new origin here, mx, ms, my, mt, x and y, s and t refer to the size of the scaling size of the particular boxes, no problem. Then we start traversing through the individual. Sides of the box here. Now, maze, of course, like I told you before, is 60 bits long, and I have the segment definition indicates that I want to address each bit individually. So if a particular bit is set, okay, let's say the left-hand side is set, then we draw the left-hand side, move the index forward. If the top is set, draw the top, drop the bottom, etc., etc., etc. And you can see going forward here, we take and draw each section here. And once we've gone to the right side of the screen here, we reset the counter we reset the horizontal counter back to 0 and increment the Y counter. So essentially trying to approximate a nested loop. And we do this essentially drawing each of the individual maze sides here. I'm going to take and optimize this as soon as I get a particular chance to. You'll see here that there are explicit words for setting variables. In this case, it's called calc. And so if you look up calc, for example, you can see that it's telling you, okay, any expressions inside calc will be evaluated, and if you use an assignment here, assigned to a particular variable, that sort of thing. And it gives you the order of operations in which things are done, which is very helpful. So moving down, so that's that. Now that we end the loop here, we take and go ahead and restore our relative origin here and our relative cursor back up to 0, 0 so that everything is normal. I did this so that I set relative drawing commands so that I wouldn't have to apply, add or multiply to get the final coordinate here. I could simply just set the relative origin of the box and draw relative to that box. It makes the code a lot easier to deal with. Anyway, so backing out, where is that particular data structure that we're reading from populated? Well, if we go back to defines, we can see segment maze, and it's the first variable, as you saw before, the first common variable. We want this to be common because we want all users to be able to have the same maze while they're playing the game. And it's, each field is 1 bit long for each wall of the maze. If we go into maze init, we can see a lot hairier code here for drawing out the maze, and the particular plan of action here is essentially to reset the maze, clear everything out to 0. Then we go through a loop, setting random bits all over, and adding walls all over the maze here. We're doing this using a command called randu, which if we do, if we look up randu or randu, we can see that it creates pseudo-random integers. First parameter is the variable to pop into. If you don't specify a variable, it's 0 to 1. If you do specify a secondary parameter, that's the range. That's the range here. So essentially, it's just a range from 1 to whatever. It's just a quick way to get a quick random number. So once you have that, we take and set those off. I take and put a little comment here to differentiate between the next section here, which goes ahead, reuses some of the local variables here again, and this time what I'm doing is knocking down walls in the maze here. I'm setting random parts of the maze here up to d bits, which d bits is currently set to 23. So 23 random bits after that point get set to 0. This is a way to try and get rid of some of the boxes inside the maze that may have shown up while we were flipping random bits on. And at this point, we're left with a maze with a whole bunch of walls taken out of it, but we still may have a few cases where the maze layout may not be ideal. So we immediately take and look at each block here. Now, block is a define that actually points to the same exact variable that maze does. The difference is that maze treats NC1 as a set of single bits. Block treats it as a set of 4 bits. So for 4 bits for each side there. So this allows me to quickly iterate through all 15 of the blocks and see whether all 4 walls of that block are set. And if they are, then I take and pick a random number between 1 and 14 to essentially take and knock down 1 or more of the walls that are currently present on that to try and keep from making enclosed spaces. Then, after that, I subsequently take and clean up the maze again. This time by taking and adding the outer border of the maze so that there's an outer wall, and as well as removing potential walls around doors so you can get out all 4 doors in every case. If a door is set, then we take and close that door off, otherwise that door is open. And we continue all the way down and we continue all the way up counterclockwise through the maze here, essentially, going upward. All the way down the bits, clearing out walls that we know we want to clear out, particularly the very center of the maze. We know we don't want to have any walls in there, so we clear that out. The right side of the maze, etc. And we keep going all the way down until we hit, 59, 60, whatever. And when we're out, we have a completed maze variable that reasonably looks like a maze. For the purposes of debugging here, I've actually put in a write statement with maze data, and what we're seeing right here is actually an embedded statement. There are a whole bunch of these for doing things like showing particular variables or changing colors while you're typing text, that sort of thing. They're enclosed in these special micro characters right here, micro 0 and micro 1 respectively. After which point, when we're done, we do a subroutine call to maze draw to draw the appropriate maze here, and then we mic out here. Now this is temporary code, just so that I could see whether or not the robots and the player would look okay inside this maze. And I'm basically picking a random number of bots, zeroing out the index, and then going through each one and picking a random spot on somewhere on the screen to place the robots. And you'll notice right here, you literally see the graphic here. That's because I literally used the font key to select the alternate font, typed that font, and used the micro key, micro bold, to specify that this would be done bold. Bold essentially makes each character, each pixel, twice as big in both directions, so 4 by 4 in each direction, making the pixels much larger than they normally otherwise would be. Writing that out, and you can see a color display here before the write, so we can make sure that the bots are currently yellow, and same thing here, 4050, to make sure that the players are currently green. In fact, if we actually go ahead and look at line number 23 here, we can see it. Yeah, there she is right there. We'll go ahead and back out because I don't want to modify it, and it's now offset here. So that's essentially the program as it stands so far. I've taken you through kind of a complete workflow of how to get your own tutor space, write your initial tutor code, how to look up things in info, how to look up things using term help for a quick reference, and just kind of a little explanation of the current code that I have running here in Berzerk, so you can get an idea of what programming on PLATO is like inside the tutor language. Now I must admit this is relatively new for me. I've only been doing this for about a week, so if I said some things wrong, please feel free to correct me in the comments. If anybody has any questions or wants to contact me, you can send me a personal note to Chuck909, TSCHAK 909. I'm in the INET-D group. So, and of course you can term talk me as well. So you can talk, okay. That's my name right there. And that's my group name right there. I'm always on the system, and I'm always willing to talk, and I can always help. And the nice thing about term talk and whatnot is that you have the invention of monitor mode, so that either I can show you something or I can look at something that you're working on, and I can talk to you in text while you're working on this to try and guide you more effectively. So with that, I hope you guys enjoyed this. If you want more, please request. I will make these videos. All right. Have a nice day.